I'm here today to talk about a paper that I recently read called Ghosts of Departed Proofs, and to talk about the ideas that it presents for creating safer APIs. But before we dive into creating safer APIs, I think it would be useful to start to think about what unsafe APIs are. So I'd first like to talk about unsafe APIs. And the slides should have changed. Okay, I'll do it from here. Cool. So, let me introduce our venerable head function. This is often the first function that we get introduced to. We have nice cute graphics that accompany it, and has a type signature, which is we take a list and then we return the first element. And I'm sort of hoping that most people today are familiar with this function. So here we ask for the head element of this list, and we get the result. And the first pattern I would like to introduce is the explosion pattern. And this is something that you might see if you call the function with an empty list. And this will usually stop the program's execution midway through. If they're lucky, they'll see a send crash report. And if they're not lucky, they won't. They'll see a stack trace. And of the two approaches that I'm going to cover, the second one being where you get a nonsensical result, which maybe you'll find more commonly in sort of the older, strongly typed languages. This one is probably the more damaging of the two, because then the incorrect result can sort of leak into the rest of the state of your application, and it'll often be hard to identify the actual source of the error. So, how can we do better? Safer API patterns for the head function. The venerable maybe type. This is sort of the one size fits all. It's sort of just slap on a maybe or an either, and then everything becomes great. There are no more runtime errors. The library author can sleep at night, safe in the knowledge that the program will just never break for them. Is this true? Is it true the library authors can just go live their life and enjoy creating more libraries on GitHub? What about the users? One second. Oh, sorry, my computer's disconnected from the internet, so I don't have my notes. What about our poor users? Because all that has really happened here is the responsibility for the failure has been pushed to the users. And for the users, this isn't great, because often they are asked to verify. So when you sort of have an API, it has certain sort of preconditions that are implied, and often they're in scenarios where they know that these preconditions hold. Like if I am creating a map or something, and I'm specifying it with singleton and saying, oh, there's this single element, and then later on in their code they're doing a lookup on that field. They know that when they use the lookup function that they're expecting the value to be there, but yet we still ask them to return a maybe. No, still on there. So, new idea. We're going to, instead of changing the result type, and what we did before is we expanded the result type to also include the nothing option. We're actually going to change the input type such that there is only possible valid outputs for given inputs. So this safe HUD function says, hey, you must give me a non-empty list, because if you give me an empty list, I might fail, and that would be annoying. And I think this brings me on to a little side note that I'd like to talk about that's sort of separate from the paper, separate from the ideas of the paper, and it's an idea about responsibility in code. Because when a function that we call hands us some responsibility, we have two choices. We can either handle it or we can pass it on. And you tend to notice this sort of heuristic that people will pass responsibility in the same direction the code they call does. So if I have a function that returns a maybe that I call, I'm very likely to also return a maybe. And there are things like the maybe and either monad, which can make the syntax for this a little bit nicer. But for some things, like if you're doing a map lookup, sometimes you don't want all these errors to, your whole big parts of your program to suddenly be in the maybe or either monad. So that also brings me on to my next sort of thought, which is around responsibility. Because when we restrict what we can do, it's easier to understand what we can do. And here we have sort of two opposite examples. We have the identity function, which is sort of the extreme case where using the type system, we've restricted it so much, there is actually only one possible implementation. And then sort of counterexamples, we have the take function, where many possible valid implementations. Perhaps if you were to pass a negative number, you might get the last nth elements of the list. And then, well, from the length function, this is returning an int. Would this ever return a negative number? Because it's length, I know that. But if it was a more complex function, then I wouldn't already have that intuition. So that brings me on to the sort of the canonical case study that's presented in the paper. It's a slightly more complex example where you have a function called unsafe merge by, that the first parameter is some comparator function, and then it will take two lists, and then it will produce a third merged list. So you can sort of imagine a fairly optimal implementation if you know that the lists are already sorted by the same comparator. So you can see in our usage here, if we call sort by on one list, passing compare as the comparator, and then sort by on another list, then we end up with these two nicely sorted lists. And then, well, let's call our unsafe merge by function that we defined with the same comparison function, and then passing our two sorted lists, we get a good result. But if, for one reason or another, a different comparator is passed, then we get a nonsensical result, and probably maybe 2 hours later when the program is still running, then only then will an exception be thrown, or this error will sort of bleed out into the rest of the application state. So let's think about the ideas that we just discussed before. If we were to slap on a maybe, our sort of one-size-fits-all approach, then this is great. But I think for a lot of users, they will see themselves using the same literal function compare and then feel very comfortable just using from just, which will give the user the same experience they had before with a runtime exception. And to implement this new merge by maybe, they will have to then add some more sort of checks in this function to make sure that one, the lists are already sorted, and two, they're sorted by the same comparator. So there's sort of two things there. There's the performance, and then the user feeling like, well, I've already made a mental proof. Why should I need to handle this case? And yes, as I said, the library author has to add more of their performance checks, and the user is left with code that's a bit slower, and then they also have to use from just. Oh, they don't have to use from just, but they will be very, very likely to reach for it. And if you look, so it is no wonder that the status quo is to put a stern warning in the docs, admonishing any user who dares to merge by what they didn't sort by. And if you look in the wild, you'll see Hackage finds 2,000 cases of lookup followed by from just. Lookup tries to be good, but the user has a reason to believe the key is in the map. And what we really want is more of a dialogue between the library author and the user of the library. So how can we take that idea and put it in a bit more of a technical speak? And the paper puts it like this: how can we reflect constraints on function input values in the function type? And this is where you start to talk about things like dependent types, which is great. It's one approach. Some of the trade-offs of this is that, well, you need to start talking about your values at the type level, and this can sometimes be quite awkward. So I think there's sort of a middle ground that we can reach that I will go on to describe. And the paper describes this idea as conjuring up a name. And this is the code that you need to care about. Let me break it down a little bit. So we introduce this named constructor that takes two parameters, this being the phantom type parameter, and then an A, which is the value that it carries. We then introduce a type alias, just sort of a slightly different syntax that's maybe a bit more convenient to use. But we don't want to just export this constructor directly, because then a user could just coerce a named A into named name of any type. So we introduce this function, a way to introduce names, that first takes a value that we want to name, and then takes a function as a parameter that says, given a named value, there is always an A such that A has that name, I think. And then in this case, we're going to coerce our A value to be matching the named type that this function will probably be inferred from this function. And then we just apply, we pass the value as an input to this function. So that is idea number one. How do we feel about that? That's almost idea number one. This is everything in idea number one. So for unwrapping, so we have values that are now named, but we actually do need to sometimes use them and actually inspect the contents of them. So we also introduce this class, which allows us to unwrap named values. And we just use the safe coerce, and all this will do is just go from a named A to an A. And this default instance also ensures that there's no sort of runtime cost to having these names. Great, that is idea number one. How do we feel about that? Good? Brilliant. This is idea number two. We introduce predicates as new types. So in this case, we can say new type sorted by, takes a name parameter, just carries around the A. And then we give ourselves an instance of the class so that we can access the A, because we don't have access to the constructor. And then how this would be used in practice, we would have our sort by function, where we would name the first parameter, which we're going to name as this type variable called comp, using the infix syntax that postfix syntax that we added. We're going to take a list of elements, and then we're going to return our new type wrapper with comp as the sort of the first type argument, and of course the same list type. And then in our implementation, we're first going to unwrap our named comparison function. We're going to call the prelude list sort by, and then we're going to coerce it such that it's now sorted by, such that it's wrapped with the sorted by new type. And then if you see down here, we actually implement or have the type signature of our new merge by function, which takes a comparator again, and then takes two sorted lists, and then returns a third sorted list. And something quite magical has happened here, because in Haskell, or I don't know if you can at all, you can't directly compare functions for equality. But what we've got here is we've ensured that these comp functions are actually all the same, which I think is something that's quite magical. And then if we look more closely at the implementation here, we are also unwrapping the sorted by lists that are passed in, and then passing them to the merge by function provided by Prelude, and then coercing them to also be a sorted by list. Brilliant. So if we wanted to compare our approaches, we started with, well, if you pass in a different comparator, then you get a silly result. We tried the merge by maybe approach. We got an exception because we passed a different comparator. And then in our approach, you can see how it would be used here. Let me just dive into this. So first of all, we're calling the name function that we use, that we have, which we're using to introduce new names, and we're passing the compare function. And then we're passing it to this little block, where GT is now our named compare function. And then we're calling sort by on our two lists, passing our compare function. And then we're going on to call merge by with that same named compare function and our two already sorted lists. And sort of the three key things are that, well, merge by could not be called with a different comparator than the sorted lists were created with. And if somebody did pass a different function there, then they would get a type error. And in this, we've actually allowed the library user to decide when and how to validate that the API preconditions are actually met, because this is sort of fairly flexible. In the other examples, they maybe would have a block of code above that would maybe be an assertion even. But in this case, they sort of have that flexibility. And the user has also achieved many of the benefits of dependent and refinement types, whilst only requiring some minor and well understood extensions to Haskell 2010. Cool. Yes?
Could you go back to that?
Yes.
One more?
Yes.
Yeah, exactly. Doesn't the first function has to sort by have an instance of that class? Because you're calling the comp.
Yep.
So you have to make an instance, right?
Sorry, this function.
This function, yeah.
We have an instance of sorted by.
It's the name that needs the instance in that call. I think it's not one from the previous slide. Named, which was introduced by Twiddle.
Okay.
Are we good?
Yeah.
Cool. And then as another additional example, you could extract the minimal element of a list according to a different comparator just by writing a function like this, which would be quite optimal. Cool. Those are the sort of the first two ideas, which is phantom type parameters and then predicates as new types. So now I'm going to move on to the slightly more complex parts of the paper. Ghostly proofs. So instead of just carrying around so the phantom type parameter that we have, it could actually be used to carry around some slightly more complex data type that represents the safety argument that the user has for their sort of right to use the API. So we introduced this proof data type that has a single constructor called QED. And I just want to emphasize that this is not a system for creating proofs about things. It's a system for the library author to be able to sort of expose that they want certain invariants to hold for certain functions. So yes, we have this axiom function, and any sort of proof that you create that says, like, well, for example, a list that has elements is also, or a reverse list that has elements is also, I can always extract a proof that it actually still has elements. So you can start sort of adding more combinatorial logic to your proofs, and because these are all sitting in the phantom type parameters, you've got no constructors needed. And if I were to show you a small sort of simplified example, you could introduce this rev sort of predicate, and then have our reverse function that says, well, given this sort of named list, if you give it to this function, then it will return a reversed version of this list. And then you can create a proof that you would use in your program like this, that just says, well, a list reversed twice is equivalent as the original list. And you would then use this as part of some sort of wider thing that you were trying to convince the library functions that you wanted to do. And yeah, cool. So I think sort of the main takeaways from this talk have been about using existential names to discuss and have conversations about values at the type level between the library author and the user of the library. we've sort of enriched what we return to the user in terms of they can sort of gain information as they access data structures, and as the on type level that has no that of course has no runtime costs. And then we've also given our users some combinators and some mechanisms for having them as requirements for their functions, so that they can actually then go and construct their own safety arguments. And then the last thing that I want to end on, because we had the boring, the boring Haskell movement is this useful? Maybe it's one approach. It does sometimes feel a bit like a sort of Haskism, where if you were to do this in a dependently typed language, then these sort of proofs would be first-class entities. But I think it's interesting to explore the approaches that we have, and maybe there are particular problems that are well suited for this approach. Thank you. I'd also quickly like to thank the author of the paper. He also has a version of this, a talk, and then some of Matt Parsons' articles where I sort of got some of the information about expanding the range and restricting the domain. Questions?
Must be a very simple question. On your second approach,
Yes.
are you able to go back to the slide? You had basically final slide on your second approach. You had something named a bit further, sorry. Was the kind of full example? A bit further.
As in
Yeah, back to one more.
this.
No, one more before that.
Yes.
So it's impossibly completely relevant. I'm just surprised that the parentheses weren't prepared.
I think I just wanted to emphasize that, and maybe I think I had probably something different there before, and then I didn't remove the parentheses. Yeah, maybe I had like a lambda that directly put there a lambda expression, but great question. Yeah.
Are you aware of someone using this technique in production code?
So I think this paper was originally inspired by the author's work on the justified containers package, which I don't know if people are familiar with. It's a way of getting proofs. You can sort of do a check to see if there's a key in a map, and then you get back a proof that it is, and then you can call a lookup function without getting a maybe returned. There is a GDP package on Stackage, which is package that has greatly improved the ergonomics of certain parts of this, so some parts of the proof handling stuff to be much more implicit. And I think they've used ideas from another paper that I can't quite remember at the moment, but yeah.
So, finally, yes, I understand about this language artwork, and the research approach for API authentication of the relation, and to some application levels. So,
Any other questions? Yes.
So this idea of extensional names, or like giving names to
Yeah.
values, it's sort of reminiscent of Scala's path-dependent types, where your types can have the name of variables in a type the same way you have value in very different types. I don't know if you looked at that.
I haven't seen that at all.
Okay.
Yeah, I think that the trick that is sort of used for keeping GT is maybe similar to what ST that uses. So yeah, that. But I'm not familiar with the Scala approach.
So practically speaking, how much more do you end up adding, and do you find that you need to browse through libraries to find the right lemmas so that you can prove?
I think I don't actually know how well this works in practice, to be honest. I did have some more complicated examples that where you can, but I think that the actual library has sort of changed a bit since that. But here's the sort of proof that I was mentioning, that a list that has elements, a list that is reversed, that originally had elements also still has elements, so we can still extract the proof that it has elements. Yes, sorry.
Okay, so there is a bit of a combinatorial problem there, right? Because you have like reverse and then, I don't know, you have double the list, which you probably gets like a double excess, and then you need to also know that doubling everything inside the list is also still iscons, and so on and so forth. So that seems to...
So yeah, there is like a general question about what do you put as the sort of predicates that is, I guess, much more domain specific. Yeah, cool.
What are the required extensions? You said
I think
extensions.
probably functional dependencies, existential types, I think.
Rank and
Rank n types, yeah. Or rank 2, yeah. Cool. Any other?